Welcome to this module on the real world applications of quantum computing. Today we are going to explore how this emerging technology is poised to revolutionize multiple industries from finance to healthcare. While quantum computers are still in their early stages, understanding their potential impact is crucial for anyone looking to work in technology, science, or business in the coming decades. Throughout this lecture, we'll examine specific use cases in finance, cybersecurity, drug discovery, and material science. We'll also discuss the significant challenges that researchers face in making quantum computing practical, and we'll consider the ethical questions that society must address as this powerful technology develops. By the end of this lecture, you will have a clear understanding of both the promise and limitations of quantum computing. This is your Professor T. Freed Muhammad, Lecture 12, Marshall University in West Virginia. To understand quantum computing, we first need to understand how traditional computers work, as we have been discussing in the previous lectures. However, every lecture I bring this topic to ground zero to make sure if someone is watching this lecture only first time, and so they know where we were at in our actual learning at West Virginia and Marshall University, and where are we at in this very moment in quantum computing. So every computer you have ever used, your phone, laptop, or tablet, processes information using bits, which are like tiny switches that can be either off, representing 0, or on, representing 1. We have extensively discussed this in the past, so if you are watching this lecture first time and you have never watched any of the previous lectures that I have given at Marshall University in West Virginia, you must watch the sequence of quantum computing lectures. All the complex tasks your computer performs, from streaming videos to running sophisticated software, ultimately come down to manipulating billions of these simple zeros and ones. Quantum computers operate on fundamentally different principles borrowed from quantum physics. Instead of bits, they use quantum bits or qubits, which can exist in state called superposition, where they are simultaneously 0 and 1 until measured. This might sound impossible if you have never heard of this before, since we are discussing this in quite a length. So this is just a summarization. So let me reiterate that this might sound impossible, the superposition, based on our everyday experience, but at subatomic level, particles genuinely can exist in multiple states at once. This property allows quantum computers to explore many possible solutions to a problem simultaneously, rather than checking them one by one like classical computers do. So let us use a concrete analogy to understand the difference between classical and quantum computing, just for the sake of summarization. Imagine you have lost your keys and you know they are behind one of the 4 doors. A classical computer would check door 1, then door 2, then door 3, and finally door 4. It might take 4 tries to find the keys. The sequential approach is how every traditional computer solves problem, even if they can do it extremely fast. A quantum computer, however, could check all 4 doors at the same time due to superposition. Instead of 4 sequential checks, it needs just one operation to identify which door has the keys. Now imagine this scales up to millions or billions of possibilities instead of just 4 doors. You can see how quantum computers could solve certain types of problems exponentially faster than classical computers. This is not science fiction. It is based on well-established principles of quantum mechanics. Today's representation of the quantum computing, as we have seen in the previous slides, is organized around four major application areas where quantum computing shows the most promise. We'll start with finance, looking at how banks and investment firms are exploring quantum algorithms for portfolio optimization and risk analysis. Then we'll move to cybersecurity, which presents both a threat and an opportunity. Quantum computers could break current encryption methods, but they also enable uncheckable as well as unhackable communication systems. Our third area is drug discovery, where quantum computers could revolutionize how we develop new medicines by accurately simulating molecular interactions. Fourth, we'll examine material science and how quantum simulations might lead to breakthroughs in battery technology, superconductors, and solar panels. After covering these applications, we will discuss the significant challenges facing the field, explore the ethical implications of this powerful technology, and conclude with both near-term and long-term future prospects. The financial industry has been one of the earliest adopters of quantum computing research, with major banks and investment firms investing hundreds of millions of dollars into quantum technology. This makes sense when you consider that financial institutions constantly deal with optimization problems involving enormous numbers of variables, exactly the kind of problems where quantum computers might offer advantages. Companies like JP Morgan Chase, Goldman Sachs, and Wells Fargo have all established quantum computing research programs. While they don't yet have practical quantum computers for everyday use, they are developing algorithms and building expertise so they will be ready when the technology matures. Let us examine some specific financial applications where quantum computing could make a real difference. Portfolio optimization is one of the classic problems in finance. Given a set of investment options, how do you allocate your money to maximize returns while minimizing risk? This sounds simple, but the mathematics quickly becomes incredibly complex. With 50 different stocks to choose from, there are trillions upon trillions of possible portfolio combinations. Classical computers can find good solutions using various approximation methods, but they struggle to find the truly optimal portfolio within reasonable time constraints. Quantum computers could explore these vast combination spaces much more efficiently by using quantum algorithms like the quantum approximate optimization algorithm. So, quantum approximate optimization algorithm is something that I would suggest you strongly to conduct research by looking at Google Scholar or by going in IEEE Explore. QAOA is something that we are discussing and researching in quite depth. Future quantum computers might be able to identify optimal or near optimal portfolios much faster than classical methods. This does not just mean faster computations, it could lead to better investment strategies that account for more variables and more complex relationships between different assets. It is important to note that we are still years away from quantum computers being large and reliable enough to handle real world portfolio optimization problems. Risk modeling is crucial for financial institutions because they need to understand how likely it is that borrowers will default on loans or how market crashes might affect their investments. Currently, banks use classical computers to run Monte Carlo simulations. Essentially, they simulate thousands of millions of possible future scenarios to estimate risk. The more scenarios they can simulate, the more accurate their risk models become. Quantum computers could potentially run these simulations exponentially faster, permitting for more comprehensive risk assessment. Fraud detection presents another interesting application. Financial fraud often involves unusual patterns hidden within massive amounts of transaction data. Quantum mechanics or quantum machine learning algorithms based on quantum mechanics might be able to identify these subtle patterns more effectively than classical algorithms. Major banks are actively researching how quantum computing could improve their fraud detection systems. Through practical applications are still in the experimental stage. The key advantage would be analyzing complex multidimensional patterns across billions of transactional data in real time. Cybersecurity is perhaps the most urgent area affected by quantum computing because it presents both an existential threat and a revolutionary opportunity. Unlike other applications, we'll discuss the cybersecurity implications of quantum computing are not just theoretical possibilities for the distant future, they are concerns that security experts are dealing with right now, even though large scale quantum computers don't yet exist. The reason for this urgency is something called harvest now, decrypt later. Adversaries could be recording encrypted communications today with the plan to decrypt them once quantum computers become powerful enough. This means that sensitive information that needs to remain secret for decades, like government secrets, trade secrets, or personal medical data, is potentially at risk right now. Let us explore both threat quantum computing poses to current encryption and solutions being developed. Most of our online security today relies on encryption methods like RSA, which is based on mathematical difficulty of factoring large numbers. If I give you the number 15, you can easily tell me that it is 3 multiplied by 5. But if I give you a 300 digit number, that is a product of two 150 digit prime numbers, even the fastest supercomputer would take thousands of years to factor it. This mathematical difficulty is what keeps our online banking, private messages, and sensitive data secure. In 1994, mathematician Peter Shor developed an algorithm that would allow a sufficiently powerful quantum computer to factor these large numbers in just hours or even minutes. This is genuinely alarming because it means that quantum computers could break most of the encryption currently protecting our digital world. While we don't have yet quantum computers powerful enough to run Shor's algorithm on real world encryption keys, experts estimate we might reach that point within 10 to 20 years. This is why governments and organizations worldwide are urgently working to develop and deploy quantum resistant encryption before it is too late. While quantum computing threatens current encryption, quantum physics itself offers a solution, and that is quantum key distribution, also known as QKD. So one of my PhD students at Capital Technology University has been working on quantum key distribution in quite length. So we'll be publishing some papers. You are most welcome to carry on looking at my Scholar, Google Scholar, and see if the publication comes in, and so you can read about that. I'll have the algorithms given in my upcoming research papers. So QKD uses the fundamental principles of quantum mechanics to create communication systems that are theoretically unhackable. The key principle is that in quantum mechanics, the act of observing or measuring a quantum state inevitably changes it. This means any eavesdropper trying to intercept a quantum communication would unavoidably leave traces of their interference. Here's how it works in practice. Two parties exchange encryption keys using quantum particles, typically photons. If someone tries to intercept and measure these photons to discover the key, the quantum states of the photons change in a way that alerts both parties into the intrusion. China has already demonstrated this technology on a large scale, launching the uh, MICIUS satellite in 2016 to perform quantum key distribution between ground stations thousands of kilometers apart. And in American, we can say thousands of miles apart. While QKD systems are currently expensive and have limitations, they represent one possible path towards secure communication in the quantum age. The pharmaceutical industry faces enormous challenges in developing new drugs. It typically takes 10 to 15 years and costs over 2 billion to bring new drug from initial discovery to market. Much of this time and expense comes from the trial and error process of finding molecules that will effectively treat diseases without causing harmful side effects. Better computational tools for predicting how drug molecules will behave could dramatically accelerate this process and reduce costs. This is where quantum computing becomes particularly promising. Molecules are quantum systems. Their behavior is governed by the same quantum mechanical principles that quantum computers are designed to simulate. Classical computers struggle to accurately model even relatively simple molecules because the number of calculations required grows exponentially with the number of atoms involved. Quantum computers, however, could naturally simulate molecular behavior, potentially revolutionizing drug discovery or and molecular design as well. At the atomic and subatomic level, particles don't behave like the object we encounter in everyday life. An electron does not orbit an atom's nucleus like a planet orbits the sun. Instead, if it exists in a cloud of probability described by quantum mechanics, when multiple atoms come together to form a molecule, the quantum interactions between all their electrons create incredibly complex systems. Classical computers must approximate these interactions, and their approximations become increasingly inaccurate as molecules get larger. Consider caffeine, a molecule with just 24 atoms. Accurately simulating all the quantum interactions in a caffeine molecule would require tracking more quantum states than there are atoms in the universe. Clearly impossible for a classical computer. Currently, chemistry simulations use various approximations and shortcuts to make the problem manageable, but these approximations limit accuracy. A quantum computer could represent these quantum states naturally using qubits, making exact simulations of molecular behavior feasible. This capability would be transformative for understanding chemical reactions, designing new materials, and discovering new drugs. The drug discovery process typically begins with identifying biological target, perhaps a protein involved in a disease, and then screening millions of potential drug molecules to find candidates that bind with that target effectively. Currently, the screening is done through expensive, time consuming laboratory experiments, sometimes supplemented by classical computer simulations. The vast majority of candidates fail, and the few that succeed must then go through years of further testing. Quantum simulation could allow pharmaceutical companies to virtually screen drug candidates with much greater accuracy before ever synthesizing them in a lab. They could predict not just whether a molecule will bind to its target, but also how it might interact with other molecules in the body, potentially predicting side effects before human trials begin. Companies like Roche and Biogen are already partnering with quantum computing firms to explore these possibilities. While we are still years away from quantum computers large enough to simulate medically relevant molecules, even incremental progress could help reduce the 10 to 15 years drug development timeline significantly, potentially by several years. So, applications in material science. So, material science is a field concerned with discovering and designing new materials with specific properties, stronger metals, more efficient solar panels, better batteries, lighter construction materials, and countless other applications. The performance of any material ultimately comes down to the quantum mechanical behavior of its atoms and electrons. Just as with drug molecules, classical computers struggle to accurately predict how new material combination will behave because of the enormous computational complexity involved. Quantum computers could enable researchers to design materials with desired properties without the expensive trial and error process that currently dominates material research. Instead of synthesizing hundreds of candidate materials in the lab and testing them one by one, scientists could use quantum simulations to predict material properties computationally, then only synthesize the most promising candidates. This approach could accelerate innovations in several crucial areas for sustainability and clean energy. Battery technology is a perfect example of where quantum simulations could make a major impact. Our smartphones, laptops, electric vehicles, and renewable energy grids all depend on lithium ion batteries. But these batteries have fundamental limitations. They take time to charge, degrade after repeated use, have limited energy density, and contain material that are expensive and environmentally problematic to mine. Researchers have been trying to develop better alternatives for decades, but progress has been slow. Quantum computers could help design new battery materials by accurately simulating how ions move through different material structures, how much energy can be stored, and how materials degrade over time. Similar simulations could help develop room temperature superconductors, materials that conduct electricity with zero resistance, which would revolutionize power transmission and numerous technologies. In solar energy, quantum simulations might lead to panels that convert sunlight to electricity much more efficiently. For catalysts which speed up chemical reactions in manufacturing, quantum computers could help design more efficient versions that reduce energy consumptions and waste in the industrial processes. Let us focus specifically on battery development to understand the potential impact. Current lithium ion batteries are approaching their theoretical maximum energy density. There is only so much improvement possible with current chemistry. The next generation of batteries might use different chemistries like lithium sulfur, sodium ion, or solid state designs. Each of these alternatives involve complex material science questions. Which combinations of materials will work? How quickly can ions move through the material? How many charge cycles will the battery last? Answering these questions traditionally requires building prototype batteries and testing them over months or years. Quantum simulations could predict these properties before any physical prototype is built. For example, they might reveal that a particular combination of materials will allow ions to flow 50% faster, enabling much quicker charging times. Or they might predict that a certain solid electrolyte design will last for 5,000 charge cycles instead of current 500 to 1,000 cycles. The practical impact would be enormous. Electric vehicles that charge in 5 minutes and drive 1,000 miles on a single charge, or smartphones that last for days and never need battery replacement. While these specific improvements are not guaranteed, they illustrate the transformative potential of quantum designed materials. Despite all the promise we have discussed, it is crucial to understand that quantum computing faces enormous practical challenges. The fundamental problem is that qubits are extremely fragile. While classical bits can be represented by robust physical systems, like whether a transistor is on or off, qubit must maintain delicate quantum states that are easily disrupted by any interaction with their environment. This makes quantum computers incredibly difficult to build and operate. Current quantum computers must be isolated from all vibrations, kept at a temperature near absolute zero, colder than outer space, and shielded from electromagnetic interference. Even with all these precautions, qubits only maintain their quantum states for tiny fractions of a second before errors accumulate. So quantum error reduction is an area of research that you can conduct study also other than QKD, which is quantum Q distribution. Additionally, there is a severe shortage of people with the specialized knowledge to program quantum computers. The field requires expertise in both quantum physics and quantum computer science. Finally, the cost is prohibitive. A single quantum computer can cost tens of millions of dollars to build and requires expensive ongoing maintenance. These challenges mean that quantum computing will likely remain a specialized tool for specific problems rather than replacing classical computers for everyday tasks. Let us get specific about the technical limitations. The problem of decoherence, when qubits lose their quantum properties, happens incredibly quickly. In most current quantum computers, qubits maintain their quantum state for only milliseconds or even microseconds. During this tiny window, the computers must perform all its calculations. It's like trying to solve a complex math problem, but your paper and pencil disappear after a few seconds. This is why quantum computers currently can only run very short programs. The temperature requirement is also challenging. Most quantum computers operate at around 0.015 Kelvin, which is minus 273.135 degrees centigrade, or about 150 times colder than outer space. Maintaining these temperatures require expensive and complex refrigeration systems. Regarding scale, IBM's current record-setting quantum computer has about 1,121 qubits, and the Google system has 105 qubits. While this sounds impressive, estimates suggest that we will need systems with millions of high quality, error corrected qubits to solve most practical problems. We are several orders of magnitude away from the goal, and each additional qubit makes the system exponentially more difficult to build and control. These aren't just engineering challenges to solve, they represent fundamental physical constraints that may require completely new approaches to overcome. As with any powerful technology, quantum computing raises important ethical questions that society must address before the technology becomes widespread. First, there is the question of control. If quantum computers can break encryption, solve optimization problems beyond the reach of classical computers, and potentially contribute to weapons development, who should have access to this technology? Should quantum computing capabilities are restricted to certain countries or organizations? How do we prevent the technology from being weaponized or used for mass surveillance? The privacy implications are particularly troubling. We mentioned earlier that harvest now, decrypt later threat, where encrypted data collected today could be decrypted once quantum computers become powerful enough. This means that sensitive information you're protecting now, medical records, financial data, private communications, might be vulnerable in the future, as mentioned earlier. There is also the question of inequality. Quantum computing will initially be available only to organizations with enormous resources. Will this create a technological divide where wealthy nations and corporations gain massive advantages over others? Finally, as with many technological advances, there will likely be job displacements. Cryptography experts, for instance, may need to completely retrain as quantum resistant encryption becomes standard. Questions to consider. The question of whether quantum computing research should be regulated is continuous. Some argue that regulation is necessary to prevent dangerous applications and ensure the technology benefits humanity broadly. Others contend that excessive regulation will simply ensure that authoritarian regimes develop quantum capabilities while democracies fall behind. There is no easy answer, but the question becomes more urgent as the technology progresses. Similarly, how do we ensure equitable access? Should quantum computing be treated as public good with governments funding public quantum computing facilities, or should market forces determine who has access? The military implications are significant and concerning. Quantum computers could potentially break the encryption protecting military communications and weapon systems. They might also enable the simulation of nuclear weapons without physical testing or optimized logistics and strategy is unprecedented ways. Some defense experts argue on this creates an arms race dynamic where nations feel compelled to develop quantum capabilities to avoid falling behind potential adversaries. Societies need to prepare for transition to quantum resistant encryption and other quantum era technologies. This includes not just developing new technical systems but also educating the workforce, updating regulations and standards, and ensuring the public understands both opportunities and risks. These are not just questions for scientists and policymakers. They affect everyone. As of 2026, we are in what might be called the early experimental phase of quantum computing. Several companies and research institutions have built quantum computers with hundreds or even over 1,000 qubits. IBM's Condor processor has achieved 1,121 qubits, and Google made headlines a few years ago by claiming quantum supremacy, demonstrating that their quantum computer could perform a specific calculation faster than the world's best classical supercomputer. However, it is important to understand what these milestones mean and don't mean. The quantum computers that exist today are not yet particularly useful for solving real world problems. The qubits they use are noisy and error prone. So, quantum noise reduction is another area that you can conduct research other than quantum error reduction. Limiting the complexity of calculations they can perform reliably, the problem Google solved to demonstrate quantum supremacy was carefully chosen to favor quantum computers and has no practical application. It was a proof of concept, not a useful calculation. Current quantum computers can run simple quantum algorithms and serve as valuable research tools, but they cannot yet optimize portfolios, discover drugs, or break modern encryption. We are somewhat in the position aviation was in during the early 1900s. The Wright brothers proved that powered flight was possible, but decades of development were still needed before commercial aviation became practical. Looking ahead to the next 5 to 10 years, we can expect steady but incremental progress rather than revolutionary breakthroughs. The most important development will likely be improved error correction techniques. Quantum computers make errors constantly because of decoherence, so researchers are developing quantum error correction methods that use multiple physical qubits to represent one logical qubit that's more resistant to errors. Better error correction will allow quantum computers to run longer, more complex programs reliably. We will also likely to see more hybrid quantum classical systems. Rather than trying to do everything on a quantum computer, these systems offload specific difficult calculations to quantum processors while handling the rest classically. This is more practical than waiting for fully fault-tolerant quantum computers. Within this time frame, we might see the first niche applications where quantum computers provide real advantages, perhaps in chemistry simulations for specific types of molecules or in optimization problems with particular structure or structures. Major cloud computing providers like IBM, Amazon, and Microsoft are already offering quantum computing as a cloud service, and this trend will likely expand, permitting researchers and companies to experiment with quantum algorithms without building their own quantum hardware. However, the transformative applications we have discussed today will mostly remain out of reach for another decade or more. If we look 20 or more years into the future, the landscape could be dramatically different, assuming current challenges are overcome. The Holy Grail is fully fault tolerant quantum computers with millions of highly, in terms of, let me reiterate, the Holy Grail is fully fault tolerant quantum computers with millions of high quality qubits. Such systems could tackle the ambitious applications we have discussed, simulating complex molecules for drug discovery, designing revolutionary new materials, breaking current encryption, and potentially enabling breakthroughs we cannot yet imagine. In drug discovery, quantum computers might reduce the development timeline from 10 to 15 years to perhaps 5 to 7 years and enable truly personalized medicine where treatments are designed for an individual's specific genetic makeup. New materials discovered through quantum simulations could transform energy systems. Imagine batteries with 10 times current capacity, room temperature, superconductors that revolutionize power transmission, or ultra efficient solar panels that make renewable energy far more economically viable than fossil fuels. The combination of quantum computing and artificial intelligence might lead to AI systems with capabilities far beyond what's possible with classical computers. Finally, we might see quantum internet, where quantum key distribution enables provably secure communication across global networks. However, it is important to maintain perspective. These are possibilities, not certainties. Many technical hurdles remain, and some of these applications might prove more difficult than currently anticipated. History teaches us that technology rarely develops exactly as predicted, but often surprises us with applications no one foresaw before. So let us summarize the main points you should take away from this lecture. First, quantum computing has genuine potential to impact numerous industries, from finance to medicine to energy. This is not science fiction. It is based on solid physics and billions of dollars in research investment from governments and companies worldwide. However, and this is second key point, we are still in the very early stages. The quantum computers that exist today are research prototypes, not practical tools. The transformative applications we have discussed are years or decades away, and some might prove more difficult to realize than currently hoped. Third, as quantum computing develops, society will need to grapple with significant ethical questions about access, privacy, security, and control of this powerful technology. These discussions need to happen now, not after a technology is already deployed. The quantum revolution is coming, even the exact timeline and form remains uncertain. As you are learning this today, this means quantum literacy, understanding what quantum computers can and cannot do, will become increasingly important regardless of your field. Whether you're studying business, medicine, computer science, public policy, or almost any other discipline, quantum computing will likely impact your career. The time to start learning about preparing for this technology is now. Thank you for your attention, and I look forward to discussing these ideas further. Happy learning. See you in the next section.